Hello and welcome to section 2.4, Measures of Variation. In this section we're going to be looking at various new terms such as deviation, variance, standard deviation. To start off, we start with the range. Okay, it's one of the most basic measures of variation. It's the difference between the maximum and the minimum data entries in the set. Okay, data must be quantitative, not qualitative, and very straightforward. We take the maximum data entry, highest minus the minimum or the lowest data entry. Okay, for example, here we have our first example. 2 corporations each hired 10 graduates. The starting salaries for each graduate are shown. These are in thousands of dollars. Find the range of starting salaries for Corporation A. Okay, so Corporation A, we would look at maximum minus the minimum. So looking at our values, looks like our maximum value will be at 37. Our minimum value, okay, would be 37. So 47 minus 37. So our range would be 10 or $10,000. Okay. Obviously, it'll help if you order your data from least to greatest. You end up with the same result. Okay, so a little side note on variation. If we calculated both sets have a mean of 41.5 or 41,500, median of 41, and a mode of 41. Yet the two sets differ significantly. Okay, difference is that the entries in the second set have greater variation. Let's take a look at a graphic in terms of frequency distribution. So we see Corporation A. Okay, notice the data is fairly tightly packed, okay, between these 3 classes, whereas in Corporation B, data is more spread out among 6 classes. Okay, so we would say there's greater variation with Corporation B as opposed to Corporation A. Okay, we start off with deviation. Deviation is the difference between the data entry and the mean of the data set. Okay, so we would define it as deviation of x would equal x minus mu for the population, and then x minus x bar for our sample data set. Okay, so sample notation versus population notation. Okay, population variance. Okay, so population variance would be the sum of your deviations squared. Okay, so every deviation you're going to square them, then you're going to sum them all up, and then you'll divide by the number of your population. Okay, and then the standard deviation is defined as the square root of the variance. Okay, so you do the calculation for the variance, you get a number, you take the square root of that number, and that gets you with your sigma or your population standard deviation. Okay, so just some notes about what these mean. So standard deviation measures the variation of the data set about the mean and has the same units of measure as the data set. Okay. Standard deviation is always greater than or equal to 0. When the standard deviation equals 0, the data set has no variation and all entries have the same value. As the entries get farther from the mean, more spread out, the value of the standard deviation increases. Okay, so just in common terms, we say that the measure of the typical amount an entry deviates from the mean. That's what we talk about when we talk about standard deviation. Okay, so it's the measure of the typical amount that an entry deviates from the mean. Okay, the more the entries are spread out, the greater the standard deviation. Okay, so some steps for finding population variance and standard deviation. First, we need to figure out the mean. Okay, so we get the mean of the entire data set or population. Then we find the deviation for each entry. Then we square each deviation, sum them all up, add up all the deviations. Okay, and then so we find the deviation, then we square each deviation, we sum them up, and then we divide by our n, by our number for our number of entries, and that gets us our variance. Take the square root of the variance, and that gets us our standard deviation. Okay. Okay, so find the population variance and standard deviation listed in the first example. Okay, so we know that our n was 10. Okay, 10 values. Our sum was 415. Okay, so we know that the mean then is 41.5. Okay, so that's important. So now that'll help us to get the deviation. Okay, so take each entry and just subtract the mean. Okay, so 41 minus 41.5. One interesting note for the deviations: if you add up the deviation in any study, it will always add up to 0. Okay, very interesting little trivia. That's why we don't use the deviation as a measure of like the sum of the deviations. Like if we were trying to add these all up and then divide by, let's say, 10 to get an average deviation, it'll never tell us anything because the sum of the deviations is always going to give us 0. Okay, so statisticians have gone through the step of doing taking these deviations, squaring them, so we get positive answers. Then, once we divide by our n, then we take the square root. Then that gets us standard deviation. So we see right off the bat why we have to go through this process. Okay, so once we get the deviations, square them. Okay, so each one, notice, gets squared. They all turn positive. Sum these all up. Right, add these all up together. Okay, we get 88.5. And then take that 88.5, divide by n, and that gets us 8.9. Okay, and take the square root of approximately 8.9, and our standard deviation is about 3 units. Okay, so population variance is about 8.9, and the population standard deviation is about 3.0, or about 3,000. Okay, for a sample, okay, similar formula. The only difference is when we come to our variance. Okay, notice the notation for variance for a sample is S squared, okay, versus the sigma squared, and we divide by n minus 1 instead of n. Okay, and so I went through the question of, well, why aren't we dividing by n? It would make more sense to divide by n. And I did a little research on it, and it turns out that using n minus 1 ends up giving us better estimates of the standard deviation and the variance when it comes to smaller numbers. And I think that has to do with if we had a sample and we take into account any outliers, any little change in those outliers can make a big difference, as we saw with the mean, etc. So similar kind of thing happens with variance. And so if we end up dividing by a smaller denominator, that would end up giving us something a little bit more true to the overall population. Okay. So we take our deviation, which is the x minus x bar, we square, we sum them all up, and we divide by n minus 1. Okay, and then we take the square root of our variance, and that gives us our standard deviation. Okay, so almost similar series of steps. We find the mean first, we find the deviation of each entry, we square each deviation, and then we sum up these squares of our deviations. Okay, and then we divide by n minus 1 to get the sample variance, and then we take the square root of the variance, and that gives us the sample standard deviation. Okay, so here we have a study of high school football players that suffered concussions. Players that recovered from their concussions in 14 days or less were placed in Group 1. The recovery times in days for Group 1 are listed below. Find the sample variance and standard deviation of the recovery times. Okay, so if you want to pause the video for a minute and try to work on it, feel free to. Okay, so now you want to, okay, so each deviation was found. We squared each deviation, we summed them all up. We came up with a sum of 39. Okay, we divide 39 by n minus 1. So we had 12 entries here. So 39 divided by n minus 1. That gets us approximately 3.5. Okay, this will be our variance. And then take the square root. Take the square root of 3.5, or if you want a little bit more precise measure, we divide it by not 12 but by 11 because we're doing n minus 1. Okay, and then the square root of 39 over 11 is approximately 1.9. Okay, so about 1.9 days. Okay, yes, and that matches. Okay, using technology to find the standard deviation. So use technology to find the mean rental rate. Okay, so this is sample office rental rates in dollars per square foot per year for Los Angeles, as shown in the table. Use technology to find the mean rental rate and sample standard deviation. Okay, so here's where you could use your calculator to help you. You could also use Minitab or Excel. Okay, so here's a typical step you would go in when you go into the TI-84 Plus. You want to go into the Stat menu, so go to Stat. And then it's the first option, you want to edit. So you want to edit a list. Okay, so let's use our first list here, L1. And now we're going to type in these data entries. Okay, so just be careful as you're going through them. So 51, 47, 33, 74, 24, 36, 41, 42, 30, 14, 11, 42, 40, 22, 35, 29, 15, 87, 35, 51, 26, 40, 36, 24. Okay, so once you have them all in, go back to Stat. You want to use your arrow key and go over to the Calc menu. And it's the first one that says one var stats, one variable stats. So hit 1. List 1 is, the list is L1, so that's good. Go down to calculate. Okay, and then it gives us our information. It says the mean is 36.875. Our sum of our x values was 885. The sum of our x values squared. Okay, here's the important part. Here's our standard deviation for the sample. So it's 17.39. They also give us the standard deviation for the population, sigma x, 17.025, etc. Okay, if you go down, they give you n, which is the number of data entries we had, which was 24. It gives our minimum value, and then it gives us some information for our box and whisker plot. We have Q1, median. Okay, it gives the median entry there. So that's the same median we use, like from median mode. That's median, 35.5. They give us Q3, which we will learn about. We'll learn about Q1, Q3. And they give us our maximum. Okay, so they give us a lot of information there. Okay, but it does it all for you. You just gotta type in the data entry. Just type in your numbers, stat, one variable stats, and it's all there. Okay. Yep, and there they have our TI-84. Yep. So it's all there. Okay, and the Excel version is there, the Minitab version is there. Okay, interpreting standard deviation. Okay, like we said earlier, standard deviation is the measure of the typical amount an entry deviates from the mean. The more the entries are spread out, the greater the standard deviation. Okay, so what do you think happens with these three cases? Here we have in the left not much variation, right? All the data values seem to be 5. Okay, mean is 5, standard deviation is 0. Okay, let's look at the middle. Mean is 5 again. Now a little bit more variation. You see it's more spread out. Standard deviation 1.2. Here the mean is 5 again. Standard deviation is even more, 3.0. Okay, so we see how standard deviation can get affected by the way the data is spread out. Okay, when it's not very much spread out, closer to 0. When it is very much spread out, far from 0. Okay, so let's take a look at this one. Without calculating, estimate the population standard deviation for each data set. Okay, so this would probably be 0, right? Looks like all the data values are at 4. And then if we're comparing 2 with 3, the standard deviation is 3, and 3 has to be more than the standard deviation in 2. Alright, and I think most people will agree. Let's take a look at. Okay, so 1. Each of the 8 entries is 4. Standard deviation is... Right, deviation is 0, so standard deviation is 0. Okay, each of the 8 entries has a deviation of plus or minus 1. Okay, right, so they're either at 3 or at 5. So population standard deviation should be 1. Okay, by calculating you can see that standard deviation is 1. Okay, and then number 3. Each of the 8 data entries has a deviation of plus or minus 1 or plus or minus 3. So population deviation would be about 2. Okay, and by calculating we get standard deviation about 2.2. Okay, good. Okay, interpreting standard deviation, the empirical rule. Hey, empirical rule, 68, 95, 99.7 rule. For data with a symmetric bell-shaped distribution, the standard deviation has the following characteristics. About 68% of the data lie within one standard deviation of the mean. About 95% of the data lie within 2 standard deviations of the mean. And then about 99.7% of the data lie within 3 standard deviations of the mean. Okay, it's a very interesting statistic, and it happens a lot, comes up all over the place in statistics, and that's why we call it the empirical rule. Okay, it's almost like a law. If it's a bell-shaped distribution, very important. Okay, so let's see what we're looking at when we call a bell-shaped distribution. Okay, this is a typical bell-shaped distribution. Okay, so here's what we're talking about. 68% within one standard deviation. Okay, so we would we would break it up like that. 68%, 34 on the one side, 34 on the other side. About 68% of your data is going to fall within one standard deviation. And then look at this, within two standard deviations, 95% of your data within two standard deviations. Okay, so you could split it up like this, another 13.5% here and 13.5% here. And then within three standard deviations, you get almost everything, 99.7% of your data. Okay, so it's 2.35% on this end and 2.35% on that end. Okay, so this is our typical bell-shaped distribution and our empirical rule. Okay, so using the empirical rule. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States, ages 20 to 29, was 64.2 inches, with a sample standard deviation of 2.9 inches. Estimate the percent of the women whose heights are between 58.4 inches and 64.2 inches. So let's take a look at how we can solve this. We know the mean is 64.2 inches. And we want to know, estimate the percent of women whose heights are between 58.4 and 64.2 inches. Okay, so if we know our typical bell curve, and our mean is 64.2, I should say. So 64.2. That means we have 34. Okay, so about 34 and 34 like this, right? So this is about 34.13%. Now, if to figure out up to where that would be, we take the 64.2 and let's take away a sample standard deviation, so 2.9. Okay, so 64.2 minus 2.9. Okay, so that gets us to 61.3. 61.3. And then do another 2.9. Oh, perfect. So that gets us to 58.4. Okay, so another standard deviation brings us to 58.4. And then the percentage that was between one standard deviation and two standard deviations is 13.59%. And so they want to know, estimate the percent of women whose heights are between 58.4 and 64.2. So that's going to be all this. So we got to add together the 34.13% with the 13.59%. Okay, so it should be roughly 47.72% of the women who have heights between 58.4 inches and 64.2 inches. Yep. We see the same data, 34.13 and 13.59, using the empirical rule. And so we add them up. Correct. Good. So about 47.72% of women are between 58.4 and 64.2 inches tall. Okay, good. Okay, Chebyshev's theorem. So Chebyshev's theorem we could use if the shape of the distribution is not bell-shaped. Right? If it's not a normal shaped curve, then we could use Chebyshev's theorem to figure out the portion of the curve lying within a certain range. Okay, so here let's take a look. This is our formula for Chebyshev's theorem. Okay, portion of any data set lying within k standard deviations, where k has to be greater than 1 of the mean, is at least this. Okay, so for example, if k equals 2 in any data set at least, and if we plug 2 into our k, so 2 squared is 4, that means we have 1 minus 1/4, which gives us 3/4, and that means at least 75% of the data lie within 2 standard deviations of the mean. If k equals 3, in any data set at least, and if you do the math here, that's 1 minus 1/9, which is 8/9, or about 88.9% of the data lie within 3 standard deviations of the mean. Okay, so remember, this empirical rule applies to symmetric bell-shaped distributions. If the distribution is not bell-shaped, or if we don't know the shape of the distribution, then we could use Chebyshev's theorem. Okay. Example. The age distributions for Georgia and Iowa are shown in the histograms. Apply Chebyshev's theorem to the data for Georgia using k equals 2. What can you conclude? Is an age of 100 unusual for a Georgia resident? Explain. Okay, let's take a look at that. Okay, so let's take a look. So from our diagram, we know that the mean is 37.3, standard deviation is 22.3. If k is equal to 2, that means we could go below 2 standard deviations. If we did that, we would be at negative 7.3. Right? So if we subtracted 2 standard deviations from our mean, we can't go to negative 7.3 as age, so we could use 0. If we add 2 standard deviations to our mean, we would be at 81.9. Okay, so using Chebyshev's theorem, we know we could say that at least 75% of the population of Georgia is between 0 and 81.9. So the age of 100 is more than 2 standard deviations from the mean. So it would probably be very unusual for a person to live this long in Georgia. Okay. Let's take a look. Standard deviation for group data. Okay, so if you have a frequency distribution, this would be the formula we would use. Again, we would find the deviation squared. We would multiply by the frequency, right, the number of entries in data set, and we would still end up dividing by n minus 1 and then taking the square root. Okay. When a frequency distribution has classes, estimate the sample mean and standard deviation by using the midpoint of each class. Okay, so that's also an important detail that we could use. Okay, finding the standard deviation for group data. You collect a random sample of the number of children per household in a region. Find the sample mean and sample standard deviation of the data set. Okay, so take a minute to pause the video, try to figure it out. Okay, here's our solution. We can first construct a frequency distribution. Okay, so keep track of all your zeros, all your ones. Okay, it happens to be 10 zeros, 19 ones, 7 twos, etc. Okay, we figure out each value and multiply by its frequency. Right, so for the 19 ones, 1 times 19. For the 7 twos, 2 times 7. Add them all up. Right, this gives us our total. Okay, so our sum divided by the number of our numbers, n, and we got a mean. Sample mean, 1.8 children. Okay, and then from there we could do our deviations. Right, so our deviations, 0 minus 1.2, negative 1.2, square it. Okay, so we get the squared value for a deviation. And then that squared value we multiply by 10. Right, for the next one, the squared value we multiply by 19. And it kind of makes sense. If we were going to do this, think about if we didn't have the classes, right? We'd have 10 zeros, and we would be doing the same process 10 times for the 10 zeros. Okay, think about this for the 19 ones. Imagine there's 19 rows of ones. We're doing the same exact thing 19 times. Okay, so it makes sense that we're multiplying by 19, and that gets us our total here. We add all these up. And then we have to take that divided by n minus 1. That'll give us the variance. N minus 1 is 49. And then we take the square root, and we see that we get standard deviation of about 1.7 children. Okay. Okay, using midpoints of classes, the figure shows the results of a survey in which 1,000 adults were asked how much they spend in preparation for personal travel each year. Make a frequency distribution for the data. Use the table to estimate the sample mean and the sample standard deviation of the data set. Okay, and here we see different classes, right? What travelers spend in preparation for personal travel each year. So less than $100, there's 380 of them. 500 or more, there's 70 of them. Okay, it looks like those are the two extremes. That's two extreme groups. And then we have in between, spending 100 to 199, there's 230 people. 200 to 299 is 210 people. 300 to 399 is 50 people. Spending 400 to 499 is 60 people. Okay. Begin by using a frequency distribution, right, to organize the data. Because the class of 500 or more is open-ended, you must choose a value to represent the midpoint, such as 599.5. Okay. Okay, so here's what our table would look like. So our classes, as we said, 0 to 99. Midpoints, okay, it's just taking our low end and our high end for each class. Right, the lower class boundary, upper class boundary, add them up, divide by 2. That gets us our midpoint. So there's 380 of these 49.5s, so multiply them. Okay, then we add these all up. 192,000 divided by 1,000, which is the number of people in the study. So sample mean is 192. Okay, next we find the deviation. Then we square each deviation. Take the deviation, multiply each of them by their own frequency, their own respective frequency. Add those up, get the sum. Divide that sum by n minus 1, which is 999. So we get, and then we take the square root. And we get 160.3 as a sample standard deviation. Okay, so an estimate for the sample mean is 192 per year. Estimate for the sample standard deviation is $160.30 per year. Okay, coefficient of variation. Coefficient of variation describes the standard deviation of a data set as a percent of the mean. Okay, so we always find it as a percent of the mean. So we take the population standard deviation divided by the mean, and then we multiply by 100 to get the percent. Okay, same thing with the sample. Take the sample standard deviation divided by the mean, and then multiply by 100. And that gets us our coefficient of variation. Okay, example, comparing the variation in different data sets. The table shows the population heights in inches and weights in pounds of members of a basketball team. Find the coefficient of variation for the heights and the weights. Then compare the results. Okay, so if you want to take a minute and figure this out. Okay, the mean height is 72.8 inches with a standard deviation of 3.3 inches. Coefficient of variation for the heights is 3.3 over 72.8 times 100, which gives us about 4.5%. Okay, let's take a look for the weight. Okay, mean weight is 187.8 pounds with a standard deviation of 17.7 pounds. The coefficient of variation, 17.7 divided by 187.8 times 100 gives us 9.4%. Okay, so now how do we interpret that? Well, the coefficient of variation, the CV, for the weights was greater than the one for the heights. So we say the weights are more variable than the heights. Okay, so there's a lot more change in the weights than there were the heights. Okay, so that's the end of our lesson. Hopefully this helps. Feel free to email me if you have any questions. Have a good day. Have a good night. We'll see you soon.